In this tutorial, we will learn how to solve application problems that have to do with optimization. Let's take a look at this problem of minimizing. We want to construct a box whose base length is 3 times the base width. The material used to build the top and the bottom costs $10 per feet squared, and the material used to build the sides cost $6 per feet squared. If the box must have a volume of 50 feet cubed, we have to determine the dimensions that will minimize the cost to build the box and the minimum cost for constructing the box. Let's take a look at a box. Let's suppose that our height is called h, our width is w, and our length is L. We know because of the problem said that the length has to be 3 times the width. So taking into consideration this, let's see what the goal of our problem is. We want to minimize the cost of the material with the restriction that the volume of the box must be 50 feet cubed. That means that I have to find the dimensions of the box that will give me a volume of 50 feet cubed and will give me a minimum cost for building my box. Now what do I need? I need 2 equations, an equation of restriction and an equation that we are going to minimize. So we have the restriction equation, which we know that it's the volume, length times the width times the height, and that it has to be 50, and the cost, which it's going to be 10 times 2 times the length and the width, because that's the cost of the top and the bottom, and 6 times 2 times the width and the height plus 2 times the length times the height, because it's the other sides. Now we have to put everything in terms of just one variable. So what we're going to do is we're going to remember that the length is 3 times my width. I'm going to take the value of my L and I'm going to substitute it into my volume. This way I will have 3W times H, and that's 50. We're going to isolate our H, so what we do next is 3W times W, we end up with 3W squared, and then we pass this right here that it's multiplying, we pass it dividing. So therefore we have that H, it's equal to 50 divided by 3W squared. Now we need the equation of cost to be in terms of just one variable. So what we're going to do is we're going to substitute both the value of L and the value of H into the equation of cost. So we have that C of W is going to be equal to 10 times 2 times 3W times W plus 6 times 2WH plus 2 times 3W times H. And if we simplify that, we end up with this function right here. Now we need to substitute the value of H in here too. So substituting H into the equation, we end up with this equation. Now if we simplify, we end up with the next thing. If we divide 48 by 3, we end up with 16 right here, and this W goes away with one of these W's. So we end up with 60W squared plus 16, that multiplies 50 over W. And simplified completely, we end up with the function C in terms of W, it's equal to 60 times W squared plus 800 over W. Now we need to find the critical points in order to find the maximum or the minimum value. In this case we need the first derivative of CW. So what we have to do is we express this equation that we already knew, we express it this way, putting our W over as a numerator like W to the negative 1. To do the first derivative, we find 60 times 2, which is 120, and we subtract 20 minus 1, that's why we end up with a 1 right here. And we multiplied minus 1 times 800, we end up with minus 800, and to minus 1 we subtract a minus 1, so we end up with minus 2. Therefore, if we do the addition of these two terms, we end up with this function right here. This is our first derivative. We're going to need this because it's going to help us find our critical points. Now, equaling to 0 and finding the points, it looks like we've got 2 critical points. The first one, it's going to be W equal to 0, but it's not a correct value for the problem because it makes no sense to talk about a box with 0 width. Therefore, this critical point is ignored. The next critical point comes from equaling the first derivative to 0. So if we equal it, we end up with this right here. 0 is equal to 120 w to the third power minus 800 over w squared. If we isolate, what we end up with is 120 w cubed, it's equal to 800 because it passed adding, and then I passed this dividing, so it's 800 over 120. If I simplify that, we end up with 20 over 3. And if we find the cube root, because in order to get rid of this exponent we have to find the cube root, we end up with w, it's equal to the cube root of 20 over 30 over 3, which that's approximately 1.8821. Now we have to check that this critical point is a minimum point. How do we find that? Remember that if we find the concavity, we can determine if it's a maximum or a minimum. For this, we will need the second derivative to find the concavity of the curve that we are working with. So the second derivative is found by the same method. We pass 120 and then minus 2 multiplies minus 800, which that gives me positive 1,600. And the minus 2, I subtract the minus 1, and that's going to be w to the minus 3. We know that whatever the value of w that we get, it will have to be positive, and we can see from the second derivative that the provided w greater than 0 will give me a second derivative positive 2. So in the interval of the positive optimal values, the cost function will always be concaved up. And if it's a concaved up value, we know that we have something like this. Therefore, the value that we are working with, it's a minimum value. That's why we can say that w, 1.8821, is a minimum cost. So all we need to do now is to find the remaining dimensions using the value of w and substituting it to find the length and the height. If I substitute into h, I end up with 4.7050, which that's my height. Into L, I find that that's 5.6463, which that's my length. And if I substitute into the function of cost, the value of w, I end up with 637.60, which that's the minimum cost that it will take for me to construct my box. Therefore, we have the following links in the box to have the minimum cost, but whose volume is 50 feet cubed. These are the final solutions to our problem. The dimensions of the box have to be height, 4.70, length, 5.6463, and the width, 1.8821. This will give me a minimum cost for constructing the box of $637.60. And this is how we come to the end of this problem, application problem of optimization.